At the end of this video, I hope that you are able to list the 4 quantum numbers and describe their significance, meaning what they signify, and relate the number of sublevels corresponding to each of an atom's main energy levels, the number of orbitals per sublevel, and the number of orbitals per main energy level. In the Bohr atomic model, electrons of increasing energy occupy orbits farther and farther from the nucleus. According to the Schrödinger wave equation, electrons in atomic orbitals have quantized energies. An electron's energy level is not the only characteristic of an orbital that has been indicated by solving the Schrödinger equation. In order to completely describe orbitals, scientists use quantum numbers. Quantum numbers specify the properties of the atomic orbitals and the properties of the electrons in orbitals. The first 3 quantum numbers result from solutions to the Schrödinger equation. They indicate the main energy level, the shape, and the orientation of an orbital. The fourth quantum number, the spin quantum number, describes a fundamental state of the electron that occupies that orbital. As you read the following descriptions and as you hear the following descriptions of the quantum numbers, refer to the appropriate columns in Table 4-2, which is found on page 104, which you will see later in this video. Alright, the principal quantum number. The principal quantum number, symbolized by n, indicates the main energy level occupied by the electron. Values of n are positive integers only, 1, 2, 3, and so on. As n increases, the electron's energy and its average distance from the nucleus increases. See figure 4-12 on page 101 of your textbook. For example, an electron for which n is equal to 1 occupies the first and lowest main energy level and is located closest to the nucleus. As you will see, more than one electron can have the same n value. These electrons are sometimes said to be in the same electron shell. The total number of orbitals that exist in a given shell or main energy level is equal to n squared. The angular momentum quantum number. Except at the first main energy level, orbitals of different shapes, known as sublevels, exist for a given value of n. The angular momentum quantum number, symbolized by L, indicates the shape of the orbital. For a specific main energy level, the number of orbital shapes possible is equal to n. The values of L allowable are 0 and all positive integers less than or equal to n minus 1. For example, orbitals for which n is equal to 2 can have one of 2 shapes corresponding to L being 0 and L being 1. Depending on its value of L, an orbital is assigned a letter, as shown here in Table 4-1, which is also on page 102 of your text. As shown in Figure 4-13, which is found also on page 102 of your text, S orbitals, corresponding to L being 0, are spherical. P orbitals have dumbbell shapes, D orbitals are more complex, and the F orbital shapes are too complex to discuss in this course. In the first energy level, n is equal to 1, there is only one sublevel possible, an s orbital. As mentioned, the second energy level, n is equal to 2, has 2 sublevels, the s and p orbitals. The third energy level, n is equal to 3, has 3 sublevels, the s, p, and d orbitals. The fourth energy level, n is equal to 4, has 4 sublevels, the s, p, d, and f orbitals. In an nth main energy level, there are n sublevels. Each atomic orbital is designated by a principal quantum number followed by the letter of the sublevel. For example, the 1s sublevel is the s orbital in the first main energy level, while the 2p sublevel is the set of p orbitals in the second main energy level. On the other hand, A 4d orbital is part of the d sublevel in the fourth main energy level. So, how would you designate the p sublevel in the third main energy level? The p sublevel in the third main energy level is designated as 3p. How many other sublevels are there in the same main energy level with this one? Well, in that 3p sublevel, there are two other sublevels, the 3s and the 3d. Moving on to the magnetic quantum number. Atomic orbitals can have the same shape, but different orientations in three-dimensional space around the nucleus. The magnetic quantum number, symbolized by m, indicates the orientation of an orbital around the nucleus. Here, we describe the orbital orientations that correspond to various values of m. Because an s orbital is spherical and is centered around the nucleus, it only has one possible orientation. This orientation corresponds to a magnetic quantum number of m is equal to 0. There is therefore only one s orbital in each s sublevel. As is shown in figure 4-14, the lobes of a p orbital can extend along the x, y, or z axis of the three-dimensional coordinate system. There are therefore 3 p orbitals in each p sublevel, which are designated as p sub x, p sub y, and p sub z orbitals. The 3 p orbitals occupy different regions of space and correspond, in no particular order, to values of m being -1, m equaling 0, and m equaling +1. There are 5 different d orbitals in each d sublevel, like you see here in figure 4-15, which is also on page 103 of your textbook. The 5 different orientations correspond to values of, again in no particular order, m is -2, m as -1, m as 0, m as +1, and m as +2. There are 7 different f orbitals in each f sublevel, but we will not see those graphically represented in this video. The spin quantum number. Like Earth, an electron in an orbital can be thought of as spinning on an internal axis. It spins in one of two possible directions or states. As it spins, it creates a magnetic field. To account for the magnetic properties of the electron, theories of the early 20th century were created based around the spin quantum number. The spin quantum number has only two possible values, a +½ and a -½, which indicate the two fundamental spin states of an electron in an orbital. And a single orbital can hold a maximum of 2 electrons, which must have opposite spins. So here we see, looking at A, the s orbital is spherically shaped, and there is one s orbital for each value of n being 1, 2, 3, and on, for the principal quantum number. We see in B, for each of the values of n, 2, 3, and 4, there are 3 p orbitals. They are dumbbell-shaped, but they differ in orientation around the nucleus. And then looking at C, for each of the values n is equal to 3, 4, 5, and so on, there are 5 d orbitals. 4 of the 5 have similar shapes, but differ in orientation, with the 5th having that wacky donut shape around the middle. And lastly, please refer to the patterns that exist in table 4-2, found on page 104 of your textbook. So, as of right now, I hope that you can list the 4 quantum numbers and describe their significance. I hope that you can relate the numbers of sublevels corresponding to each of the atom's main energy levels, the number of orbitals per sublevel, and the number of orbitals per main energy level, which you can again refer to the table 4-2 to practice your pattern skills.